Can you turn a messy relation into a perfect mirror? Welcome back to our JEE Main series. Today we are tackling question 3, a classic counting problem from the sets and relations. Let A is equal to this set and R is a relation on A defined by xry if and only if 2x is less than equal to 3y. Let L be the number of elements in R and M be the minimum number of elements required to be added in R to make it a symmetric relation. Then we need to find the value of L plus M. Let's think sharp and ensure your logic is bulletproof. But before we touch the numbers, we need our sharp tools. So, relation, we are looking for all ordered pairs x, y from set A that satisfy the condition, which is 2x less equal to 3y for every possible pair from A. And a relation is symmetric if x, y belonging to R implies y, x belongs to R, which means the mirror image yx must also be there in R, then only the relation is said to be symmetric. First step is to find L, which is the number of elements currently in R. So let's scan through set A and we will take one value of x at a time. So the values of x are 2, 3, 5, 7, 9 and let's see what are the corresponding values of y from this A. So obviously we will choose those values of y which will satisfy this relation. So for x equal to 2, we need 4 less than equal to 3y. Now if we put the values of y from A, we will see all these numbers be it 2. So 3 times 2 is 6. So obviously 4 is less than equal to 6, true. So if y equal to 2 is true, definitely all the values of y which are greater than 2 will also be true. So all the values of y work and hence the number of ordered pairs we get for x equal to 2 is equal to 5 because 2, 2, 2, 3, 2, 5, 2, 7 and 2, 9 are all the pairs that will belong to R. Next, for x equal to 3, we have the condition 3 times 2 which is 6 less equal to 3y. So if I put the first value, I am getting 6 less equal to 6 which is true. That means all the other values will also be true. So these are the possible values of y, which means again the count is 5 because 5 such ordered pairs I will get for my R, which is 3, 2, 3, 3, 3, 5, 3, 7 and 3, 9. Next for x equal to 5. So we need 10 less equal to 3y. So if I put 2, so 10 is less equal to 6, false. If I put 3, we get 10 less equal to 9, again false. So if I put 5, I'm getting 10 less equal to 15, which means all those y which belongs to 5, 7, 9, they satisfy the condition and hence I'll get 3 such pairs from here. 5, 5, 5, 7 and 5, 9 will belong to R. For x equal to 7, similarly I'll check by putting all the values over here and we will see that only these values of y work. So again, number of ordered pairs is 3. For x equal to 9, this is the condition and the possible values of y are 7 and 9 because you can see 3 times 7 is 21. 21 is obviously greater than equal to 18. 9 times 3 is 27, obviously greater than equal to 18 and hence we will get 2 ordered pairs from here. So adding them up we get total L equals to 18. Now next step is to find the value of M. M basically represents the number of new elements that we must physically add to the set R to satisfy the requirement of symmetric relation. Symmetric relation means if xy is present in R, then its twin yx must also be present in R, right? So we need to see how many of them are missing. So M is that count of the ordered pairs that are currently missing. And also remember pairs like 2, 2, 3, 3 are already symmetric. So let's look back at our table and ask which of these pairs don't have their mirror image in the table. So if you look at x equal to 2, we have the elements 2, 2, 2, 3, 2, 5, 2, 7 and 2, 9 in R. So that means there are 5 pairs for x equal to 2. Out of these 5 pairs, how many of the pairs do not have their twins? That is the count of M. So let's check for their twins to see if they break symmetry. So 2, 2 and 2, 3 already have twins in the table because 2, 2 is its own twin, and in the second row you can see 3, 2 already belongs to R, right? 3, 2, 3, 3, 3, 5. But look at 2, 5, 2, 7 and 2, 9. Does the relation contain 5, 2? 5 when x is 5, y cannot be 2. Or 7, 2 when x is 7, y cannot be 2. Or 9, 2 when x is 9, y cannot be 2. So if you check the table for x equal to 5, 7 and 9, you will see that y equal to 2 is never an option because it fails this condition. So because these 3 pairs are lonely and missing their twins, so we have to add 3 new elements to the relation to fix the symmetry, and that is why the count for M is 3 in this row. Similarly for the next row, 3, 2, which already have a twin, we can see in the first row only. 3, 3 is its own twin, but 3, 5 do not have a twin because 5 when x is 5, y is not 3. Similarly 3, 7 and 3, 9 also do not have their twins. So that's why the count is 3 for this row as well. So when x equal to 5, we have 5, 5 which is its own twin, 5, 7, so 7, 5 is also present, but 5, 9, the mirror image of this is not present, 9, 5 is not there. That means from this row, only one pair does not have mirror image, that's why the count of M over here is 1. For x equal to 7, 7, 5, 5, 7 is already there, 7, 7 is its own mirror image, and 7, 9, 9, 7 is already there. So count is 0 because all the pairs over here have their twins. And for 9 as well, 9, 7, 7, 9 is present, and 9, 9 is its own twin. Again, is 0. So the total value of L and M are these. Question asked for L plus M. So L is 18, M is 7, so 18 plus 7 which is 25, and if you look at the option, that brings us straight to option D, 25. And this proves that in JEE, your organization is your best weapon. If you skip the table, you skip the marks. And mastering these boundary conditions is what separates the toppers from the rest. If this step-by-step breakdown helped you visualize the logic, hit that subscribe button for Think Sharp Alley. I'll see you in question 4.